Also, I was trying to transcribe. ¿Tienen algún vídeo o algo del plan segundo? No.
No. Salgo y entro. Déjame que salga y entre de compartir. Is it working now?
I think it's also trying to do
Yeah, I accepted something. Maybe it is drawing the captions below.
I put something on. See if you can see it better. I like it for Alright.
For me, it's okay.
Okay. All right. Welcome, everybody, and welcome back to a series of seminars. Today we have here Pedro de la Torre Luque. He currently works at Universidad Autónoma de Madrid. And well, Pedro actually, he studied his master's here in the University of Granada. Actually, he had fond memories of IEA, and he was coming here for his master lessons and so on. And then afterwards, he did the PhD at INFM Bari. And then he moved to the Oscar Klein Institute in Stockholm. And since a couple of years ago, he works as a Juan de la Cierva Fellow at the Universidad Autónoma de Madrid. And 15 minutes ago, we learned that he actually got Ramón y Cajal, so congratulations. Final resolution was as follows. So in case you want to check. And well, today he's gonna talk to us about galactic cosmic rays and diffuse gamma rays. And also the neutrinos.
And also neutrinos.
Please, Pedro.
Thank you very much. It's a real pleasure to be here after 8 years that I was here for last time. I have to thank you a lot for the invitation also. Thank you very much. I would like to come here every year actually. So I hope I will convince you that this is interesting. Okay. To put some context in the talk, I want to stress that from very recently we have been able, for first time, to have measurements of the gamma ray emission in the galaxy, PeV electron volt energies, PeV energies. This is amazing, okay? Along with this, 2 years ago, more or less, the IceCube collaboration presented the first ever measurement of galactic neutrinos, from the galactic plane. This is another very important achievement, also covering the energy range of TeV to PeV, teta electron volt to peta electron volt. with this talk, I want to show you that these measurements, these observations can be extremely useful to help us understand how cosmic rays propagate in different parts of the galaxy and what is the origin of the most energetic cosmic ray particles in the galaxy. What are the sources accelerating these particles to such huge energies, okay? And something that I want to leave very clear is that cosmic rays, neutrinos, and gamma ray diffuse emissions are tightly correlated, and they offer complementary views to similar phenomena or the same phenomenon, okay? And to start, I have to mention the Fermi-LAT experiment on board of the Fermi satellite, because it has made us, or it has allowed us to understand the gamma ray sky at J-electron volt energies much better with unprecedented precision, let's say. Today, Fermi, or the Fermi-LAT experiment, has observed around 7,000 sources, point-like sources, and about 100 extended sources in the sky. In addition, with some studies have allowed us to understand that there is also an isotropic emission coming from extragalactic sources that are so far away that they become an uniform background, conforming what we call the extragalactic background light. Okay? Once you subtract emission from sources and the extragalactic background light, what you end up with is the diffuse gamma ray emission from the galaxy that follows essentially the disk of the galaxy, and you can see some structure coming from the gas of our own galaxy. And this emission is directly correlated with cosmic rays with the density or the fluxes of cosmic rays, because these cosmic rays are generating these diffuse emissions. The diffuse sky, let's say, is composed mainly by three components, three different contributions. The first process, Bremsstrahlung, that is the breaking radiation also, is the result of interaction of electrons with the gas in the interstellar medium, and this is why it follows the nice shape of the gas distribution, okay? Then we have also inverse Compton emission that comes from the upscattering of photons in the interstellar radiation fields of the galaxy by cosmic ray electrons, okay? And the most important one, the hadronic emission. The hadronic emission is the dominant one above the GeV, at least, up to very high energies. And as you see, it also follows the distribution, the spatial distribution of the gas, okay? This is mainly the result of cosmic ray nuclei, and mainly protons, colliding or interacting with the gas in the interstellar medium and producing pions. And as you know, pions, if they are neutral, will eventually decay into photons, producing the diffuse gamma ray emission. And similarly, you may imagine that these kind of interactions will produce also charged pions. And these charged pions will generate, eventually, by decay, the neutrinos that will form the diffuse neutrino emission in the galaxy. So we have these two diffuse emissions coming directly from the same kind of interactions. This is why they are directly coupled, no, or correlated. But on top of these distributions that emerge from cosmic ray interactions, we also have another component that is what I will refer to as unresolved source emission. And this emission comes from the fact that our instruments or some sources bright at a level that is below the threshold of detection of our experiments. So we cannot detect, really identify a source there. And in the end, this emission from these sources is misidentified as part of the diffuse background emission, okay? In the end, you cannot see that there is a point-like source there, so you misidentify as part of the background, okay? This component is not the part of the truly diffuse emission, but is another component of the diffuse emission we have to take into account. And in the case of neutrinos, since we do not have the resolution to observe sources, independent sources, all sources will be part of this unresolved source contribution, okay? I will go to that later. The problem is that since cosmic rays follow essentially power loss in energy, the gamma ray emission that they produce also follows power loss, and this means that fewer gamma rays will reach your detector as we go to higher energies. And this is a limitation for satellite-based experiments, as example Fermi, okay? And this is essentially the reason, because until very recently, we only have upper limits of the diffuse gamma ray emission in the galaxy above the TeV, okay, the tera electron volt. And this is also at the same time the reason, because to detect this kind of gamma rays, we need to build experiments with very large collection areas, and we need to build ground-based telescopes. For example, CTA, that you are probably very familiar with, has, etc. But since recently, and in particular since 2021, we have had the first detection of PV gamma rays ever, coming from the Tibet experiment, okay? After this detection, we had other two experiments providing also data that covers the diffuse galactic emission from the TeV to the PV. So this is extremely good to be used in combination with Fermilab data to understand what's going on in the galaxy with these charged particles, these cosmic rays producing secondary emissions, okay? So we have a wonderful chance to compare our models that are built using the precise spectral data on cosmic rays and compare with what we observe up to the PeV range in gamma rays. Here there is a problem, unfortunately, and it is that you can see this data is spectrally very precise, but it is very limited to the fact that the only information from cosmic rays that we have is local information. We only can measure cosmic rays that come to the Earth, okay, or come to our experiments. And this is a very important limitation because we expect that these particles are propagating in different ways in different zones of the galaxy, okay? In particular, well, this propagation is usually modeled as a diffusive process, characterized by a diffusion coefficient that is essentially a power law, and theoretically, we expect it to follow some spatial trend also. Why? The reasons are multiple, okay? Theoretically, we observe that the magnetic field, both intensity and direction, is changing in different parts of the galaxy. The plasmas are not the same in different parts of the galaxy. Even the distribution of sources changes. And in general, this means that the galaxy itself is an inhomogeneous place, okay? And this makes us expect that the diffusion process will be different depending on where you are in the galaxy. And this is a problem because essentially the flux of high energy cosmic rays follow a power law. That is the convolution of two power laws. One is a power law with a spectral index alpha that comes from the injection of particles from sources, okay? And the other one is the power law coming from the propagation, from the effect of propagation in the particles, and therefore the spectral index is the delta of this diffusion coefficient. And this is a problem because delta can be different in different parts of the galaxy, and for sure the flux could be different in different parts of the galaxy. The problem, in the end, we don't have access to this information, the spatial behavior of the diffusion coefficient, and in general, we simply neglect it and model everything as uniform propagation of particles in the galaxy. However, here one can think the other way around and use gamma ray observations to try to infer how is the propagation of cosmic rays in different parts of the galaxy. And this is what we have tried to do using a phenomenon that doesn't have a clear explanation, and it's observed by Fermilab in the diffuse gamma ray emission, and it is a progressive hardening of the power law or the spectral index of the power law describing the diffuse emission. This is what I try to represent here in this plot, where you have distance from the galactic center and a spectral index. The spectral index representing the flux, the diffuse emission observed by Fermi, okay? And as you can see, feeds to the data reveal that this trend is changing, and changing significantly already. The fact is that this has been observed in different energy windows and by different methodologies. So this is something that is clearly real, let's say, okay? It's not an artifact of a particular modeling. The problem is that it doesn't have an explanation that makes everyone happy. It's very difficult to put all the ingredients here to reach a real answer. But in this case, we can reproduce, one of the hypotheses is that we can reproduce this trend if we implement a diffusion coefficient whose spectral index changes towards the center of the galaxy. This will reproduce this kind of behavior. Other people also suggest that the the emission from result sources can be more important there, and therefore you could have you could mimic the effect of inhomogeneous diffusion. However, I will be focusing on the diffusive idea, no? on the explanation of this as being originated by inhomogeneous diffusion in the galaxy. Okay. And this is what we did. We implemented a diffusion coefficient that is inhomogeneous, and by order zero, we simply adjusted the delta, the spectral index of the diffusion coefficient, as being linear dependent to the distance from the galactic center. These are here. And with this, implemented it in the software Dragon to code to solve the propagation of cosmic rays. We could use Fermi data to obtain what are the values of how this delta A parameter changes, or to adjust in the end the behavior of delta in different parts of the galaxy. Here is what I try to show you in this plot, where the different colors indicate different locations in the galaxy, different longitude windows, all in the galactic plane, from something farther away, very far away from the center, to the very center of the galaxy in black. And the solid line, well, and the lines represent two models. One is the scenario that I call gamma optimized model, and it is the inhomogeneous diffusion scenario. The other one is the homogeneous uniform propagation scenario that I call base model here, okay? And you can see how far away from the galactic center, they don't differ significantly, or they are mostly the same, while at the very center, the gamma optimized model in homogeneous diffusion scenario let us reproduce the data better, okay? Well, just for completeness, here I leave you the parameters that get to reproduce, let's say, this trend observed in gamma ray emission from Fermi. But after that, we have to model the injection of cosmic rays, this alpha parameter that I was talking about before. Okay, and the way we do this is by fitting local cosmic ray observations, and since we need to make to evaluate or to predict the gamma ray emission up to PV energies, we need to have into account cosmic rays up to the knee in the galaxy, up to 10 to the 9 gigaelectron volts. It's a lot of energy. And the way we do, as I said, is reproducing this data. These are local cosmic ray data, protons in particular. And as you can see, above the PV, the data start to be very uncertain, okay? And in particular, we see like two kind of trends. One trend favoring isotope measurements, while the other trend favoring Cascade Grande data measurements, okay? I will explain you in a moment what are the other lines here. So what we did to take into account this uncertainty at high energies is to build two models that encompass and take into account the differences between these two kind of trends. One is what we call the max model, that essentially follows the measurements from AMSO2, and we extend this power law up to the point that it meets the isotope data, and it follows isotope data. Then we have the mean configuration, the mean model here, which follows AMSO2 data and then damper data, and the damper break here, and it joins very well then with the flux measured by Cascade Grande delay. Therefore, here we have within each scenario, homogeneous and inhomogeneous propagation scenarios, we have two configurations, max and mean model, that differ only in the injection spectrum of cosmic rays. Okay, and keep in mind the max model follows isotope data, while the mean model follows measurements from Cascade Grande. This will become clearer why I want to stress this distinction later. And okay, and once we have this, we have all the ingredients. We just simply need to convolve with gas densities, with interstellar radiation fields, with magnetic fields to make a prediction on what will be the gamma ray and neutrino emission at very high energies and compare with the data that we have. Here, in the beginning, I'm going to focus on gamma rays, and in particular, I want to show you what is the comparison with Fermi-Lat data, again, GeV energies. Here, to make this comparison fair, we have to sum source emission to our diffuse model taken from the catalog, extragalactic background light emission, and then we also used a model of a result emissions in Fermi that comes from Catherine Ekberg and Konstantin Stepa, some works from them. And it is important to mention at least that this contribution, you can see here, this dot line here, is expected to be very subdominant with respect to the data observed by Fermi. These black points are the data of Fermi. Okay. Another thing that is important or is relevant to stress here, well, here in this plot you see all the components that come into this model. You have, for example, inverse quantum Bremsstrahlung pi zero emission as a dotted, that yellow line. And as you can see, the contribution from pi zero emission, at least in the galactic plane, dominates this emission. And this is also true up to very high energies, okay? Then, for example, you can see that the emission from sources, that is this dotted dashed line, is also subdominant, quite subdominant, maybe at 10% or so. Okay, and then when doing a comparison with Fermi lab data in different parts of the galaxy, we find an overall satisfactory agreement, okay? Even though we are not fitting Fermi data in all the regions of the sky, okay? We are trying to put a model, putting some ingredients there, but not directly fitting Fermi lab data in the galaxy, okay? But what is more important here is the difference between this red-brown line and the black line. That is the difference between the gamma-optimized inhomogeneous diffusion scenario and homogeneous diffusion scenario, the base model. Okay, as you see, this difference becomes more important in the center of the galaxy. And this is very relevant, especially because this difference will grow with energy. So that when we extend our predictions to PeV energies, we find that at 1 PeV in the center of the galaxy, we expect the inhomogeneous scenario to let's say, to predict a diffuse emission that is a factor of a few higher than in the case of the homogeneous scenario. And this is very important. This is important especially also for the CTAO or SWGO that are gonna be very precise or are gonna provide very precise measurements of the center of the galaxy. And this is a relevant effect to take into account, okay? This possibility. And for sure, now that we have data, higher energies, we have to compare and see if one of these scenarios is whether it is or not favored by the data. This is exciting, and sorry, this was exciting, especially when the Tibet collaboration announced the first detection of PeV photons, because actually in their paper they directly say that their measurements are favoring a non-homogeneous diffusion scenario, okay, or a non-homogeneous scenario of the distribution of cosmic rays in the galaxy, okay. And to that, you can sum the fact that the LHAASO collaboration presented the results saying that the flux is 3 times higher than what they expected. Both things are not totally true, okay, or not well founded, let's say. But it's clear that the community is trying to understand what's going on with these measurements here and if they favor or not one scenario or the other. Okay, let me now compare with the different instruments with Tibet-ASγ and LHAASO, starting with LHAASO data. Okay, LHAASO provides data in 2 different regions of the sky. In the left, the inner region, what they call the inner region. In the right, what they call the outer region. In this outer region, we don't expect to see any difference between the different inhomogeneous scenarios because we are very far away from the center of the galaxy. While in the inner region, we can expect to see some differences between both scenarios because we are clearly closer to the center of the galaxy. Here, Fermi-Lab data are shown in green, and these blue data are LHAASO data coming from 2 different detectors, WCTA and kilometer 2 array. Okay, kilometer square array, whatever it is. Solid line represents the gamma optimized model, so homogeneous diffusion, but in the mean configuration following cascade grounded data. And max model is the prediction using the isotope spectrum. Okay, and as you can see in both cases, it seems that the that the data follows perfectly the predictions from this mean model, ruling out or disfavoring at least the max model, injection of cosmic rays following the measurements of ice top data. Okay, and here you can say, well, maybe this is clearly indicating that this is favoring inhomogeneous diffusion, but this is not, because there is a trick, okay? And it is the fact that to derive these measurements or to obtain this data, the LHAASO collaboration has to apply a mask in the sources that they observe, okay? They have to remove the emission in a big region around the sources in order to subtract the only diffuse emission and not contamination from sources, okay? And the result is this huge mask, that is actually removing almost the two entire inner degrees of the galaxy, which removes a lot of valuable information, and therefore it removes also the differences or blurs the differences between the inhomogeneous and homogeneous scenarios. This is what I want to show you in these two panels in the left here, where I'm showing essentially the same as before, but now I'm including also these red, brown lines that represent the base model, so the homogeneous scenario. And as you can see, even in the inner region, the differences between base and gamma optimized inhomogeneous and homogeneous diffusion scenarios are not enough to say that these data are favoring or not any of these scenarios. Okay. In the right, I'm showing you that the difference in the inner region without applying any mask to the diffuse emission is larger. You can see that the difference between black and brown lines in the inner region of the galaxy is larger, okay? While in the outer region, this difference is very, very low or negligible at least. The data point shown here is the total emission measured by LHAASO. And again, the only thing that this tells us, probably because of the math that they are applying, is that the max model is disfavored, completely disfavored, while we cannot say anything clearly favoring inhomogeneous or homogeneous diffusion scenarios, okay? But I want to stress a couple of things about these measurements. For sure, it's incredible to have these measurements, because a few years ago, this wasn't even thought to be possible to have such a good measurement, and this detector has been wonderful for that. And one remarkable thing, at least for me here, is that they found a 2 sigma hint. This is just a hint, nothing statistically significant, favoring a different power law of the diffuse emission in the inner region and the outer region. Again, this is only a hint, very low, well, not even a significant difference, okay? But it is suggestive already. The second thing I want to mention here is that only comparing the data with our diffuse models produced from cosmic ray interactions in the galaxy, this diffuse emission, truly diffuse emission, seems to be dominating the total flux that LHAASO observes. Okay, so at least for the LHAASO observations, the contribution from our result sources seem to be subdominant. Okay, and this is a point that is important, because once you or if you derive your data or their data without applying any mask, you must have into account some contribution from a result source. Okay, this contribution can be important, but in this case, after applying this mask of LHAASO, it seems that the truly diffuse emission from cosmic ray interactions is the one that dominates. And result sources can be very important. I mean, this contribution can be very important at high energies. And in fact, there have been papers, this one, showing that the Tibet data can be explained with a dominant contribution of unresolved point-like sources, okay? And I stress here the fact that they are modeling point-like sources, okay? The problem, you need to rely on some extrapolations that are difficult, and different predictions will, and it's very difficult to have a robust estimation of this contribution from unresolved sources, okay? I was stressing the fact that that this estimation is for point-like sources. And this is because there is another kind of sources that can contribute significantly to the unresolved sky, let's say, diffuse contribution, the unresolved diffuse contribution. And this is because of the fact that extended sources also can be misidentified and cannot be identified well as independent sources, and sometimes they become part of the diffuse emission. Okay, our telescopes cannot distinguish them from the background because they are very big, and in the end, you interpret these flags as coming from diffuse emission. Okay, one of the most popular cases of extended sources is the case of TB halos. Okay, this emission from TB halos is mainly inverse compton emission having generated from electrons originated around pulsars. Okay, and the extension of these sources can be maybe between 20 and 30 parsecs, this order of magnitude. But what is relevant here is that it has been shown that the contribution of TB halos could be quite relevant in the diffuse high energy sky. However, again here, different people doing different assumptions have found completely different predictions, and this makes this quite uncertain. Okay, there is another promising candidate contributing to the diffuse gamma ray emission that are young massive stellar clusters, and here we have an expert with us, because these are extended sources that have been observed at very high energies, and in fact it was shown that they can have a very relevant contribution at high energies depending on the assumptions, etc. However, again here, the uncertainties in order to do a prediction that is robust is extremely challenging, and we need many more observations. But with all this, my point is that unresolved sources can be very important. So we have to take them into account. And now when I will show you my results comparing to Tibet and hot data, you will see that this contribution is not negligible anymore, as in the case of LHAASO. Okay. Okay, here you have in the left comparison with mainly Tibet data, and in the right with HAWC data. These are two regions where they provide these measurements, but they are not so close to the galactic center to make differences between the homogeneous and inhomogeneous scenarios very clear. So the difference between them, the two scenarios of propagation, is very low, and we still cannot tell anything clearly significant favoring one or the other scenario. But they can teach us very interesting lessons about the role of unresolved sources. For example, here, in the comparison with Tibet, left plot, the Tibet data are this purple data. Again, the lines represent the diffuse gamma optimized emission, the black lines, and the cyan lines represent these diffuse emissions plus the contribution expected from unresolved sources that come from this paper from Christopher Egner and Francesco Calore. And what we find here, you see that the contribution from unresolved sources is not negligible at all, and it can be as high as 20% in this window of the galaxy. Okay, an important point that I forgot to mention is that unresolved sources depend on the experiment observing them. Depending on their sensitivity, you will identify more sources or you will misidentify more sources, depending on the threshold of detection. Okay, and when comparing with hot data, that is here represented as a brownish reddish band, the situation we find that the contribution from unresolved sources can be even larger. You can see the difference. Well, this magenta line is the result of summing our gamma optimized models to the unresolved sources coming from the prediction coming from this model. And in this case, the unresolved source contribution, at least from our results, seem to be quite important, up to the level of 40 to 50%. Okay, and this is very important. However, HAWC, that is super promising, this measurement in particular wasn't very refined, to say it in some words. They needed they used a template to derive this data, assuming a power law behavior, single power law behavior, and they weren't able to provide any measurement of the systematic uncertainty. However, in July, in the last ICRC, they have shown a very important upgrade of these measurements. And this is really, really relevant because they are covering here the inner galaxy. They are reaching measurements to the very center of the galaxy. And this is really relevant when you want to find evidences favoring one or the other scenarios of diffusion propagation. Okay. Here they used, well, they improved many things. For example, they used a more sophisticated model or analysis for subtraction of sources, and they also made use of different templates model and a better assessment of the systematic uncertainties involved. And the results is what you see here for latitude profile and longitude profile here, and they compare with 3 different models. The black models are essentially models featuring homogeneous diffusion in the galaxy, while the cyan one is the gamma-optimized mean model with a small tweak, small change, okay? And as you can see, the data suggests that you need a huge, or well, an important increase in the flux towards the galactic center, okay? Again, here we need to account for the contribution from the resource sources. So we cannot conclude that this is solely due to the propagation scenario, okay? So this is, let's say, a hint going in the favor of this kind of inhomogeneous scenarios, but still, given that the contribution from the resource sources is so difficult to evaluate, we don't have a clear proof that it favors inhomogeneous diffusion. And in the end, closing up this part, it means that only from gamma ray data, although they are these data are wonderful and they are providing a lot of information very quickly, we cannot tell that which propagation scenario is favored. They are significant, statistically, let's say, compatible under some assumptions in the end with gamma ray data. But the case is that neutrino measurements can offer a smoking gun here. And this is especially relevant because in the end, as I said, IceCube got almost a 5 sigma measurement of the neutrino emission from the galactic plane. So we could also use these measurements, although very uncertain at the moment, to draw some conclusions about different propagation scenarios. Okay, that the one thing that I want to say here is that they made use of different templates to evaluate the fluxes that you see in this panel here, and the one with the best fit was the pi zero, what they call the pi zero model, inspired on Fermi-Lab data. Okay, in comparing this with our predictions, again, black lines represent gamma optimized mean and max. Here you have the measurement of this or the estimation of the flux by IceCube using the pi zero best fit model. And here with another template, the Kragamma 5, that is, let's say, an old version of the model that I'm presenting here of inhomogeneous diffusion, you can see that this model agrees quite well with the best fit neutrino measurement by IceCube. Okay. However, again here, uncertainties, you can see that the different fluxes from using different templates change a lot. So we have to be very careful with the systematic uncertainties here, and we are still, let's say, seeing the beginning of neutrino of galactic neutrino astronomy. Okay, but this is very interesting because, as you can see, there could be very little room for contribution of sources to the neutrino emission from the galaxy. And this is very interesting because this could mean, for example, that most of the sources in gamma rays could be of leptonic nature. And in fact, many sources observed by LHAASO are actually associated with the leptonic sources, but well, this is too soon to say anything about that. But this can bring really nice information about the origin of, or let's say, the nature of the emission from pevatons in the galaxy. Okay. Going again to the comparison between inhomogeneous and homogeneous scenarios, these neutrino measurements are super interesting because you can see in this left plot that is essentially the same measurements as in the previous slide, but with another scale of energy, that the spectral shapes of what the flux that you expect in one and the other scenario of diffusion is quite different. So if we reach a good sensitivity, good precision in these measurements, at some point we could disentangle between the different origins scenarios, let's say. Okay. Here I want to show you also another region, the galaxy, that is very interesting, but this time this comes from measurements from Antares. Antares is very good to observe the galactic center because they don't have contamination from muons or atmospheric neutrinos going to the detector, because let's say the center of the galaxy is in the direction that has to cross all the okay, neutrinos are transparent, well, the Earth is transparent to neutrinos, so they don't have that much contamination coming from the muons generated in the atmosphere. Okay, and as you can see, also in this region that is very close to the galactic center, or at least encompasses a good portion of the galactic plane, the difference between base and gamma optimized model is already significant. Okay, so this and the following measurements by kilometer 3 net will be extremely important to understand the nature of these flux. I think I have still some time, maybe 3 minutes. The last thing is that going a little bit further, these are some preliminary measurements, and in fact, in the last analysis, the error bars were a little bit higher. But okay, this is. It's very interesting, the study of the central molecular zone. The central molecular zone is a region in the galaxy that is very big and has a density of gas of more than 100 times higher than the normal interstellar gas in the galaxy. Okay, and in this zone, you expect to have a huge rate of interactions of cosmic rays with the gas, simply because the density of gas there is 100 times higher than in any other part of the galaxy. And in fact, you can see how different models, different assumptions, either, well, max and mean, and the gamma, or on the scenarios of propagation, change a lot, are very different. Okay. However, here, in particular, in this study, what we are finding is that we need an important contribution coming from sources emitting neutrinos, at least in this region. Okay, so this is just to say that neutrino astronomy is super promising, and there are specific targets that could give us very, very nice information. So I want to conclude here. Oh yeah, I think we are seeing like how the gamma ray astronomy up to the PV is opening a window for understanding many open problems in cosmic ray physics, and also in gamma ray physics for sure, and neutrinos. Right now, although there are hints, there is no clear, significantly speaking statistically, there is no significant hint in favor of any diffusion scenario, but for sure it seems that neutrinos will be very important in the next decade or even later. For sure, these kind of scenarios are also very interesting for CTA-O and SWGO, and have to be investigated. And probably some of you already take an eye on that things. And a last thing I want to mention is that the fact that we are taking into account or considering the possibility of inhomogeneous diffusion in the galaxy could change also the predictions that we have, or the models that we have for other observables. For example, we are studying synchrotron emission. Synchrotron emission or the background synchrotron emission from cosmic ray electrons could be very, very different in the different scenarios of diffusion. Okay, this is due to that the process is also anisotropic. Okay, but for example, one can go even further and try to say, okay, but if this is true, if we actually have inhomogeneous diffusion in the galaxy that is theoretically well motivated and there can be hints favoring it, what is the impact of this in indirect dark matter searches with cosmic rays, with antiprotons, with positons, for example? Okay, so those are things that we have to investigate and are important problems, but interesting topics to take a look to. So I think that's all. Thank you very much.
Thank you very much for this nice overview and for showing us the results. And now let us open for questions. Pedro? Okay, Stefan?
Maybe I have a curiosity. So maybe you say that I missed it. So you see that IceCube also LHAASO has released this new measurement without the masks. It's a bit frustrating because every year LHAASO publish a new measurement.
And preliminary, that then it can be different. Well,
yeah.
I don't know if you have compared with the data.
That is very, very slightly higher, but not that much.
For me, no one is in LHAASO here. It doesn't make sense.
Right.
I tell you why. When I was comparing these models, I mean, I cannot understand that when subtracting only sources instead of having the mask, you obtain the similar level of flux. The reason is simply when you apply these diffuse emissions to whatever thing you do, you get at least a factor of 1.6 difference in the flux that you expect, simply because you are removing an important part of the galactic emission. So I don't understand how they can get something so similar if you are actually removing the center of the galactic plane.
This is for the measurement that was published to be 3 times larger.
No, this is because they have presented the data but doing another procedure. This time subtracting the flux, not masking the sources from sources. And they obtained compatibility with a small, maybe 20% different.
Compatible with the previous
Exactly.
result that is much higher.
That is lower because they are masking a big portion of the galaxy. The problem is that the difference is 20%, while just taking into account diffuse emission, you get a factor of 1.6 difference. So for me, I would wait for the publication.
Yeah.
May. I think it.
Maybe you want?
Thank you for that answer. When we were starting to talk about the neutrinos and we were showing, well, somehow, comparing the results of the neutrino detected with your model and then the result from LHAASO again, that seemed really pointing more to the quantum origin of the emission that they are detecting. I didn't quite get your point.
Sorry, yeah.
There's a contradiction here or differences
No.
in evidences.
Mhm.
So what's
Okay, what I mean here, okay, this here, the only sources of emission is neutrinos from cosmic ray interactions and neutrinos coming or generated close to the source. Okay, neutrinos from the sources. What happens is that if the sources, for example, a pulsar won't generate neutrinos, I mean, because you are not accelerating protons. Well, there are some papers that say that it may be the case, but the main emission in gamma rays is from inverse Compton. But if you have inverse Compton, you don't have hadronic production. So what I mean here is that since we are so almost saturating the measurement already of IceCube, there is little room for the emission from sources, from neutrinos produced in source. And this may be due to the fact that most of the sources can be leptonic in gamma rays, in very high energy gamma rays. So they won't generate this hadronic emission at the same time. But I mean, this is a model, things have to be refined. Maybe the next observations will contradict me. But in the end, we don't have still a huge catalog of sources at the PEB. Okay, we have, I don't remember, maybe 20 sources detected by LHAASO, maybe more. So we still need a survey of the pevatrons to understand what is the origin of the highest energies, the highest energy cosmic rays and emission.
I have a question on Zoom.
Okay.
Maybe Etienne wants to say it out loud, or you want to type it, Etienne?
Hey, I can you hear me? I can say it out loud maybe.
Can you hear him on your computer? I don't know.
Sorry, it was inside, muted. Now?
Hello, can you hear me? Okay, that's fine. I'll type it.
Hold on. Etienne, can you speak?
Hello, can you hear me now?
Oh my god.
Maybe
Sorry.
No, it's now. No, it's now.
Better to type it.
Yeah, I'm typing now.
Okay, thank you.
Okay, in the meantime, I had you can close your
Yeah,
speaker. I had a question. So in the end, you mentioned that well, when you're assuming inhomogeneous diffusion, you also have other observables that you need to reproduce, right? You mentioned synchrotron emission, but this is probably not the most difficult one. during the whole presentation, I was thinking, I mean, you have in cosmic rays, you have all the spectrum of all the species, the boron to carbon ratio, the beryllium 9 to beryllium 10 ratio, everything, and everything is so difficult to be. So with in homogeneous diffusion, can you get a satisfactory fit of all?
That is really difficult.
Yeah.
I mean, the point here would be to observe what is the morphology. The main point here is that this theory of inhomogeneous diffusion all comes from the fact that cosmic rays are expected to propagate anisotropically when you are going like parallel to the magnetic field lines, or you are moving perpendicular to the magnetic field lines. Since in the center of the galaxy, by the shape of the magnetic field, most of the lines point upwards, okay? They will diffuse significantly different to how they do it, and you can see features or a change in the spectral index of the synchrotron emission in those parts. What happens?
That would be a way to validate it.
Yeah, we are working on that. No, in fact, in the prediction, you see how the shape is different of the synchrotron emission. We are also taking a look to polarized emission, etc. But it's complicated. Not so simple as making a simple comparison.
But one curiosity for the people that are saying that you can have different spectra in the inner and outer galaxy only with unresolved sources. Is this because the unresolved sources in the inner galaxy have a different?
Sorry. No, well,
different
here the point.
in the outer galaxy?
No, here the point would be if towards the center we expect to have more sources towards the center, either resolved or not resolved. And the spectrum coming directly from sources is not convolved with propagation, so it would be harder. The spectrum is like e to the alpha instead of e to the alpha plus delta, so harder. So you can, if more sources are dominating more progressively as you go to the center of the galaxy, you could see a kind of hardening. That is more or less the point. But
the ones in the back, they are also the gamma ray emission we receive. It is also not convolved
if it is subdominant,
okay.
But this has to be robustly done. Okay, this is the idea.
Okay, but the spectrum from unresolved sources in the inner and outer galaxy in principle should be the same.
Yeah, yeah. If you don't have inhomogeneous diffusion, the spectrum should be the same. Yeah.
Okay, thanks. Maybe we can get the question from it.
Question. Etienne writes, thank you for your presentation. It was very clear and interesting. I am curious if you have had any comments regarding the parallels between the limitations in the high energies and the confusion limit in the radio regime, especially at low frequencies, where our inability to distinguish between clouds of point sources introduces a noise component. Do you think that there are grounds for some joint characterization of the inverse problem?
Oh, thank you very much again. Let me read the question just to be sure I fully got it.
Oh, yes, you could also repeat it.
Sorry. I'm working on a similar thing. Basically, in each case, there are some. I would say no. At this second question. In the first question, I have some things, but maybe it's because I understood your question. I didn't understand well your question. But there could be ways. There could be ways in radio to also distinguish between different mechanisms of propagation. The problem is that we don't understand the propagation of cosmic rays in clouds. I will need to understand better what is the
So
the-
I think we don't get exactly what you are asking.
yeah, please. This can be very nice. Thank you. I'm sorry.
Chat offline.
Yeah. Please email me or we can meet at some point.
Guillem has a question, maybe we can.
I'm very sorry.
Hi, Pedro. Thank you for the enlightening talk. I have a question, maybe it's a misunderstanding. You are talking about the differences with distance to the center of the galaxy. However, you plot the galactic longitude. So it is the projected distance. So when you are looking towards the
Totally.
very center, actually the propagation would cross half of the galaxy because we are pretty far away from the center. So how do you disentangle the true effect of the distance from the projected?
Yeah, wonderful. Thank you very much. In fact, this is why we need, sometimes we use analytical approximations to do this, and you cannot do it analytically because you have all the science integration, etc. And even though you have to integrate over the line of sight and you have it, you will see towards high angles, let's say, much less or a different behaviors than when you go closer to the center. Because in the end, you are scanning over a larger distance from the center. If you are looking, let's say, at the sides, at longitude 100 degrees, to put it, you are still mapping high distances from the center. So in the end, let's say, it is compensated in such a way that you are, as you look at the center of the galaxy, you are also performing the line of sight integral in average for distances that are closer to the center than when you are observing
This
to the
is
sides.
slight different, not so
Yes,
strong as it was the.
if you can pinpoint every point, the difference would be huge. This is why the effect is subtle, because in the end, the observations is what we have.
And actually, when you plot the galactic longitude, you see a small difference. While when you plot on galactic latitude, you see a huge difference towards the very center.
Yeah.
Because when you go away from the galactic plane, of course, there is nothing there.
Totally. I agree. Yeah, this is why the effect in the end, observational effect, is more subtle than one could like. And this is also very interesting because when studying this kind of behavior for high latitudes, we are watching different behaviors of diffusion to the ones that we see in the. So that could be also a kind of explanation for the difference that we are seeing. Thank you. Thank you very much.
Okay. Are there more questions for Pedro?
Yeah, I was about to answer something similar to the question. But when you got from the latitude, that was restricted to a range in longitude degrees.
Wonderful.
So, I mean, we are contaminated by local arms, these kind of things. So how you deal with that? The local arm.
Well, for sure, here we try to have into account that the injection, well, for protons, let's say, it does not make much of a difference when you predict their emission to be like radially symmetric, their emission, or following the spiral arms. Okay, it can be some effect of stochasticity. This is still something that is investigated because it can have some effects. In the models, in the end, you try to be as realistic as possible. But we cannot be always that realistic. So also the people try to make the measurements in places that could be more sensitive to something. For example, here you avoid the very center of the galaxy in latitude because of the possible presence of Fermi bubbles, other structures that can be significant there. So in the end, what we can do is to try to be as realistic as possible in the modeling. That is possible because we have different observations of the gas, etc., and then try to find optimal regions where to compare with. Also,
we're going to maximize the signal to noise.
Yeah, to avoid, in this case, to avoid other possible sources that can be significant.
Well, I was thinking, I mean, there was maybe a naive presentation, but you mentioned that one of the sources could be related to the background cluster formation in these countries. So they are completely different whether you go
Yeah.
to the center or the other parts of the galaxy or around the spiral arms. So I was wondering what I mean.
Yeah. For this case, I would say first of all we would need observation of independent transforming regions, and I think there is a lot of ongoing work on that. While this kind of let's say mapping looks more to the high scale or large scale behavior of the diffuse emissions. So yeah, to understand the cumulative behavior of these sources, we would first need to have more measurements of independent transforming regions. Thank you for the question.
Just small comment. I mean, this here is very limited, very instrumentally limited. And this is an observatory that is located in the northern hemisphere. And even if you are able to almost reach the galactic center, as you can see here, the statistical uncertainties are very large. And so you select the best region that is accessible to you. If you build the same in the southern hemisphere, that is this SWGO, then you would have a perfect coverage of that region and you will be. Okay, so are there any other questions, Pedro? Otherwise, please continue in.
Yeah, I'm fine. No?
Perfecto, sí, sí, sí.
Yeah.